Hi, everyone. Thank you for coming to my talk. And I'm very excited today to share with you our recent effort on using light-based system to enable air-water communication and sensing in support for underwater robotics. So I started this lines of research by talking to my colleagues in underwater robotics. And he looks at the problem of the use of multiple robots for ecological survey and environmental monitoring. And I learned that a big challenge of the problem is the coordination of these robots. It's very beneficial to have an aerial drone that provides a bird's eye view to facilitate such collaboration. And in order to facilitate that, it's essential for the drone to be able to communicate with and sense these underwater robots. And that turns out to be a non-trivial problem. And you might immediately think of some simple options. Right? You can have the robot periodically resurface to allow the sensing and communication with the drone. However, it will interrupt the current task of the robot and not efficient. Another option is to set up an infrastructure on the water surface. So that can be a network of buoys or boats. They serve as relays to enable the sensing and communication between these two. However, setting up the infrastructure has a non-trivial logistical and deployment overhead. So what we really need is a way for direct communication and sensing between the aerial drone and underwater robots. So what are the options? Option number one is to consider radio frequency signals. Right? So Wi-Fi, LTE, these are widely popular on the ground. And also recent research has shown they can actually also be used for enabling sensing. But in this context, the radio frequency signals will suffer from severe attenuation in the water, so they are unable to achieve reasonable distances for most applications. Another mainstream method is to use acoustic signals. However, based on physics, acoustic signals will be bounced back at the air-water interface, so they are unable to achieve the direct link between the drone and the robot. And with this in mind, we turned our attention to light. It turns out light is the perfect medium in this context. It can efficiently pass the air-water interface with minimum energy loss. So naturally, it gives you a bidirectional way of sensing and communication. And even better if you consider laser light. For laser light, most of the energy is concentrated in a very narrow wavelength range. So what it means is you can pick the wavelength with the smallest attenuation in the water to extend the range. And lasers are fast. You can enable gigahertz level modulation speed, so perfect for providing a high bandwidth communication link. So in this talk, I will present you two projects along the line. The first is M-Flight, looking at the communication aspect with laser light. And another is Sunflower, that enables direct air-water localization. And then we'll begin with M-Flight. So in M-Flight, what are the practical challenges here? The first one is coming from wave dynamics, right? Laser light is directional. So in the presence of waves, the link can easily become misaligned and unavailable. The unavailability can go up to 70% of the time. Not useful for most applications. And another challenge is to deal with beam steering, right? For the drone to talk to a robot in arbitrary location, it has to steer the beam. However, existing beam steering methods are either too bulky or too expensive. And finally, ambient light is always the enemy for any light-based systems. Especially in this case, outdoor sunlight can be pretty strong, around 100,000 lux. So it can easily saturate the sensor, make it unresponsive to decode data. So we address those challenges in flight. We presented a portable laser link to enable the bidirectional communication, and we augmented with ultrasonic sensing elements to sense the wake condition and adapt the link accordingly. So now I will give you the highlight of the key elements in the framework. So at the transmitter side, right? So the key challenge again is to enable beam steering. The common method uses gimbal. It can give you a full hemisphere beam steering. However, the granularity is pretty coarse and it's very big. It's too big for the drone to carry around. And another method is MEMS mirror. So these are portable tiny mirrors. It can achieve very fine grain steering. However, it has a very narrow steering range, no more than 14 degrees based on our research of existing MEMS mirrors on the market. So this is too narrow for practical applications. So in order to address this issue, we proposed to combine these coarse and fine grain methods to get the benefits of both. Essentially, we are utilizing a fisheye lens to expand the steering range of MEMS mirror. So most of you are familiar with fisheye lens. It's used in cameras to concentrate light coming from the full hemisphere to a small image plane. Based on the symmetry of light propagation, you can use it in the inverse direction to allow incoming light rays from a narrow angular range to be expanded to the full hemisphere. And that's exactly what we did here. We added a fisheye lens in front of the MEMS mirror. We also added the triplet lens to correct the incident angle for the fisheye. So now as the laser beam goes through each component, the mirror steers the beam in a narrow range, which will be further expanded to the full hemisphere. So that's perfect. And at the receiver side, the key problem is to extract the weak laser light in the presence of strong ambient light interference. And to give you a sense of the challenge nature of the problem, here we show the relative intensity distribution for the visible light spectrum. Here we compare the laser light to sunlight. You can see for laser light, the emission profile is pretty sparse, right? All the energy is concentrated in this center wavelength, 520 nanometers. You can see it's a green laser. And in comparison, the energy of sunlight spans across the whole visible light spectrum. Now, if you take the integration and compute the signal to noise ratio, it's miserable. It's lower than minus 13 dB, unable to give you any communication capability. And to address the problem, we actually utilize the sparsity of the laser light emission, and we added an optical bandpass filter to filter out the energy from the wavelength and really concentrate on the energy from the laser wavelength. So that allows us to boost the signal to noise ratio to more than 4 dB, and that's sufficient for basic modulation schemes. So now with the communication link in place, let's look at the ultrasonic sensing element. And the problem, as you remember, is to deal with wave dynamics, right? It can cause misalignment. If you easily expand the beam to deal with the issue, it will lead to a waste of the energy. So instead, we're proposing adding a sensing component along with the transmitter so that it can proactively sense the wave condition and then compute the optimal laser beam direction to reach the receiver. So in order to do wave sensing, we will consider ultrasonic signals. And the reason is actually mentioned earlier, right? So based on the physics, ultrasonic waves are bounced back at the air-water interface. So that's perfect for sensing the air-water interface, and it's a bidirectional solution as well. And specifically in the system, we used the ultrasonic sensor array. So basically, each sensor is going to sample the depth or the height to the water surface. And then we aggregate these discrete samples and feed them into a wave model. The wave model can then interpolate and reconstruct the wave condition. And in this project, for simple illustration, we use the bicubic surface model. This is a very basic and a popular model in computer graphics. For more sophisticated waves, we can easily replace it with other models. So it's a pretty generic framework. And it all sounds great, but one problem is the sensing delay. So all these sensors operate in the same frequency. So what it means is they can't sample the depth simultaneously, and they have to do that sequentially. And that can lead to a sensing delay up to hundreds of milliseconds, too slow to adapt to fast waves. So to address these issues, we propose a forecasting method. So instead of waiting for all the sensor readings to be ready